Welcome to The Explainer, where we treat the Cambridge Physics exam not as a random collection of scary facts, but as a system of predictable patterns waiting to be decoded. I like to call this approach the Matrix, decoding exam reality. Now, if you were sitting down to take this exam, whether that's the classic 0625, the combined sciences like 0651 and 0652, the O-level 5054, or even if you're building foundational skills for your A-level 9702, you might feel like you're staring at an endless, intimidating wall of equations and definitions. Imagine a timer ticking down. The pressure's on. Let me introduce you to two very typical students we see literally all the time. First, there's Alex. Now, Alex works incredibly hard. Alex overloads on raw physics facts, memorizing every single definition in the textbook word for word, but absolutely panics when asked to actually analyze a novel, unfamiliar situation. Then, on the other end of the spectrum, there's Sam. Sam is fast, Sam rushes through calculations, skips steps, and completely misses the actual requirements hiding inside the examiner's command words. You look at their papers, and it's just a sea of red pen marks. Both Alex and Sam are working so hard, but they are both losing massive amounts of marks. Why? Because they think the exam is just a memory test. It's not. There is no single perfect paper. They're only patterns. Once you learn to see the code behind every single question, you transition from memorizing to mastering. You become a strategist. Okay, let's dive into this and look at exactly how we are going to hack this exam together. Here is our tactical agenda for today. First, we'll map out the blueprint. Second, we'll decode the language of physics. Third, we'll master precision and errors. And finally, we're hacking motion graphs. Let's get right into it. Section 1, the blueprint. This is where we map out the battlefield. Okay, look closely at this matrix because you need to notice exactly where the absolute bulk of your grade lives. Papers 3 and 4, the theory papers, hold a massive 50% of your overall grade. That is literally half of your entire IGCSE writing on short answer and structured questions alone. The multiple choice papers hold 30%, and your practical assessment, whether that's paper 5 or the alternative to practical paper, paper 6, holds the final 20%. Here's the truth that students like Alex miss. Relying on basic rote recall will absolutely not work for that massive 50% chunk. To hit those top grade boundaries, you can't just list facts. Your answers must be perfectly structured to hit assessment objectives 2 and 3. That means handling data, manipulating formulas, and proving your experimental logic. How do top students do this? They use the PEEL framework: point, evidence, explanation, link. Every time you see a high-mark question, you don't just brain dump. You make a clear point, provide the physical evidence or formula, explain how it applies, and link it right back to the command word. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel on your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 2, the language of physics. We're talking physical quantities and their units. Listen, every physical quantity in the universe is made up of two distinct parts, a number and a unit. When you see a distance of 10 meters on your exam paper, what you are actually looking at is 10 times m. And here is a massive cheat code for your exam, something that will instantly level up your problem solving. You must treat symbols like m for meters or s for seconds exactly like variables in an algebra equation. Think about it. M isn't just a convenient label you tack on at the end of a sentence because your teacher told you to. It is a mathematical entity. Just like 10x means 10 multiplied by x, 10m means 10 multiplied by meters. Once you start treating your units algebraically, combining them, canceling them out, and multiplying them becomes incredibly logical. You literally cannot get the final formula wrong if your algebraic units line up perfectly. Let's look at a live example of how top students structure their working, and I want you to spot the exact mistake our rushing student Sam always makes. We're going to do a quick find the flaw challenge here. In the incorrect version, the student writes, speed equals 10 divided by 2 equals 5 meters per second. Do you see the flaw? Strictly speaking, 10 divided by 2 equals 5. It does not equal 5 meters per second. Stripping the m and s out of your intermediate working makes the math fundamentally structurally incorrect. Examiners hate this because it shows a lack of logical flow. Now notice the correct version. The red pen marks transform to green check marks. Speed equals 10 meters divided by 2 seconds. The 10 divided by 2 gives you the numerical 5. The m divided by the s gives you the fraction m/s, therefore 5 meters per second. It is perfectly balanced algebra. Leaving units out of your intermediate steps is a prime way to confuse yourself and bleed for easy marks when the multi-step calculations get way more complex in paper 4. Always write the unit. Always. Building on that algebraic foundation, the exam is constantly testing your grasp of scale. In the real world, and on this test, you aren't just going to see meters and seconds, you are going to see scientific notation and standard form prefixes thrown at you to trip you up. You absolutely must instantly recognize standard form prefixes. Giga with a capital G means a billion, or 10 to the power of 9. Mega is a million. Kilo is 1,000. Going smaller, milli with a lowercase m is 1/1000th. And micro is 1/1,000,000th, or 10 to the negative 6. When you see a gigawatt or a microsecond in a paper, you shouldn't pause, you shouldn't hesitate, you should instantly know exactly how many zeros you are dealing with. Translating these prefixes properly into your algebraic equations is a non-negotiable skill for passing those tough extended theory papers. If you miss a micro prefix, your final answer is off by a factor of 1,000,000. No partial credit is going to save that calculation. But knowing the math isn't quite enough. You really need to visualize these scales in your mind's eye. Let's look at mass. The SI base unit of mass is the kilogram. Knowing that a ton is 1,000 kilograms, which is roughly the mass of a medium-sized car, gives you a solid mental anchor. A kilogram is about a standard bag of sugar, a gram is a banknote, a milligram, which is a millionth of a kilogram, is roughly the mass of a human hair. Why does visualizing this actually matter for an exam? Because it gives you a built-in, subconscious error detector. If you were calculating the mass of a small wooden toy block in a paper 4 question, and your answer comes out to 4 tons, your brain should immediately scream that something went terribly wrong in your math. It's a block, not a truck. Visualizing scales helps you instinctively verify if your calculated answers actually make sense in reality, stopping you from handing in absurd answers. Section 3. Precision and Errors. This is where we master laboratory instruments. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, welcome back to the Matrix. When you are in the lab, or when you are answering an alternative to practical question on paper 6, you will inevitably be shown instruments. Rulers, micrometers, or these vernier calipers right here. Examiners want to see that you know how to use them with absolute, unshakable precision. And let me tell you, the #1 trap they lay for you, the one that catches out thousands of students every single year, is the dreaded zero error. So what is a zero error? A zero error happens when an instrument gives you a reading when it actually shouldn't. It's a false starting line. Imagine a digital bathroom scale. Nobody is standing on it, it's completely empty, but the dial clearly says 0.1 kilograms. That is a positive zero error. If you then step on that exact scale and it reads 46.2 kilograms, that is not your actual mass. To get the true value, you must identify that baseline error and mathematically subtract it from your final reading. 46.2 minus the 0.10 error equals a perfectly corrected measurement of 46.1 kilograms. You must always check the instrument's starting point before you trust the final reading. If you just grab the final number and run with it, and you don't correct the zero error, your entire downstream calculation for density or force or whatever complex multi-step thing the question is asking will be completely wrong. It's a cascading failure, all because you didn't check the zero. Here is another incredibly high-yield precision trick, this time specifically for measuring short time intervals. Let's say you need to find the period of a simple pendulum, which, as a reminder, is the time it takes for one complete swing back and forth. If you try to use a stopwatch to time just one single swing, human reaction time is going to completely ruin your data. It takes you a fraction of a second to realize the swing started and click start, and another fraction of a second to click stop. Your data is instantly garbage. To neutralize this fundamental flaw, top students use a very specific strategy. They measure the total time for 25 complete swings. If 25 swings take exactly 55 seconds, you simply take that 55 and divide it by 25. That gives you 2.2 seconds for one single swing. By averaging the time out over a large number of oscillations, that annoying human reaction time error becomes statistically insignificant. It gets spread so thin it doesn't matter. This is a classic, heavily tested Cambridge question, and this exact logic is how you secure full marks on it. Section 4. Hacking motion graphs. Get ready for some high-speed visual data extraction. Let's start this section with a core, undeniable concept: acceleration. Acceleration simply means an object's velocity is actively changing. It could be speeding up, it could be slowing down, or it could even be changing direction. To calculate it, you identify the exact change in velocity, which we represent in physics with the symbol delta V, and you divide it by the time it took for that specific change to happen. Because you are taking velocity, which is already in meters per second, and you are dividing it by time, which is in seconds, your final resulting unit becomes meters per second squared. Notice how we are treating the units just like algebra again? The s moves to the denominator and becomes s squared. It's all connected. Let's do a 60-second visual data scan challenge. Look at this visual. If you see an acceleration of positive 3 meters per second squared on an exam paper, you need to decode it immediately in your head. What does that abstract number actually mean in the real physical world? It means this specific vehicle is increasing its velocity by 3 meters per second every single second that ticks by. So if it starts at 12 meters per second, 1 second later it is traveling at 15. Another second later it's at 18. If it continually accelerates at this exact rate for 5 full seconds, its velocity will have increased by a grand total of 15 meters per second. Understanding the physical reality behind the math stops you from just blindly plugging random numbers into a calculator and hoping for the best. You actually understand the car's journey. Now for the ultimate exam hack in this syllabus, translating these kinematic concepts directly onto speed-time graphs. The examiners love to give you a graph and ask you to extract physical data from it. There are 2 unbreakable golden rules you must lock into your brain right now. First, the gradient, or the physical slope of the line on the graph, is exactly equal to the acceleration. A steep upward slope means high acceleration. A flat horizontal line means 0 acceleration. The speed is perfectly steady. Second, and this is the one that rushing students like Sam always forget, the area physically shaded underneath the graph line is exactly equal to your total distance traveled. You don't need a complex kinematic formula to find distance. You just need to calculate the area using basic geometry. Let's do a speed writing challenge right now in our minds. 30 seconds on the clock. How do we find that area perfectly using the Peel framework to explain it on paper? If the graph shows a steady speed, the area under the line forms a simple, flat rectangle. The distance is just the base times the height. That's simply the time on the x-axis multiplied by the speed on the y-axis. Point, evidence, explanation. If the graph shows a constant acceleration from rest, the line goes up diagonally, forming a triangle. To find the distance traveled there, you use the formula for the area of a triangle. 1/2 multiplied by the base multiplied by the height. Whether it's a simple rectangle for steady speed or a triangle for uniform acceleration, that basic middle school geometry provides the exact distance traveled in meters. It is a beautiful, elegant system once you see the pattern. There is no guessing. Before we wrap up this explainer, I want to leave you with a final test to check your new mastery of the system's code. Look at the screen. Which of these quantities is actually larger? Is it 2 kilometers or 2,500 meters? Is it 2 tons or 3,000 kilograms? How fast can you convert those prefixes in your head without a calculator? Well, 1 kilometer is exactly 1,000 meters, so 2 kilometers is 2,000 meters. That means 2,500 meters wins easily. 1 ton is exactly 1,000 kilograms, making 2 tons 2,000 kilograms. So 3,000 kilograms wins that one. If you can consistently view these Cambridge exam papers not as a terrifying wall of confusing facts, but as a completely predictable matrix of algebraic units, simple geometries, and distinct command words, you don't just survive the test, you master it. You decode the reality. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.